When a crowded alkyl halide is treated with a small base, alkene products are formed through an elimination process. This is a concerted bimolecular reaction, which we will call the E2. Zaitsev's rule will apply with the more highly substituted alkene being isolated as the major product. In this reaction, the strong base attacks the substrate, deprotonating at the beta position and forming a pi bond as the leaving group breaks off. This all happens in one step, and that step is known to be bimolecular since it is dependent upon the concentrations of both the base and the substrate. The reaction occurs through a transition state as shown, and deprotonation can happen at either beta carbon to give two regioisomeric alkenes. From experiment, the bimolecular rate equation indicates that this reaction only has one step. This must mean that the base removes the proton from the beta position, the pi bond forms, and the leaving group breaks away, all at the same time. This process is therefore described as being concerted. We use the dashed arrow here to describe going up a single reaction barrier to the transition state, which then collapses to product. The E2 is overall described as a concerted, single-step reaction. The transition state at the top of this rate-determining step features the following: concerted formation of an oxygen to hydrogen bond, the breaking of the C to H bond, the formation of the carbon to carbon double bond, and the breaking of the carbon to bromine bond as the bromide is leaving. The driving force for this reaction is the transfer of negative charge from the unstable oxygen in the base to the much more stable and larger bromide anion. The double bond is formed, in this case to give the more highly substituted Zaitsev alkene as the major product. Alternatively, concerted deprotonation on the right-hand side of the substrate will produce the minor, less substituted Hofmann product. The transition state on the way to this product has fewer electron-donating alkyl groups to help stabilize the developing sp2 hybrid carbons. This makes the transition state higher in energy than the corresponding Zaitsev process, so this product is formed more slowly. Putting the arrows together to explain the formation of alkenes. Since the alkyl halide is crowded at the alpha carbon, the base cannot act as a nucleophile and go through the SN2 process. Instead, the base attacks a beta hydrogen, which allows the negative charge from the base to be transferred to the halide leaving group. The result is a stable anion, the halide, and an alkene. If more than one type of beta hydrogen is present, regioselectivity is possible, with the Zaitsev isomer being favored. Cis and trans stereoisomers may also be possible. Overall, when a crowded alkyl halide that possesses at least one beta hydrogen is treated with a strong base, elimination occurs through the E2 mechanism to produce alkenes. The advantage of this method over the E1 pathway is that most alkyl halides will participate. Also, since carbocations are not formed, there will be no products of rearrangement. The regiochemical outcome of an E2 reaction is predictable, which is very useful in synthetic applications.